Hello everyone, today your Igor Gravity Engraving channel Krasnodar will also be posting these videos on the Typal channel. If you're wondering why it's called Typal, it's a blend of two words, type and people. So I combine those two words into one, type of people. Great! So today we'll talk about laser sources and emitters. What's the difference between them? We'll do a quick overview of the options, covering lenses, components, pumping methods, derivatives, lifespan, resources, and more. But we'll keep it at a high level. For those still figuring it out, this video will explain it all. Now, a quick ad break. Our company sells fiber laser markers, as well as components for fiber lasers and carbon dioxide lasers. We have tubes, lenses, and mirrors, all the consumables you need from time to time. Phone numbers are in the description, along with links and catalogs. Check them out and find what you need. Our prices are very competitive, and we accept all payment methods. As usual, let's get started. First, I want to talk about fiber lasers, specifically semiconductor diode lasers. A fiber or ytterbium laser uses pump diodes, but the actual pumping happens within the fiber optic cable or waveguide. In diode lasers, semiconductors directly emit a photon spectrum that goes straight to the lens to focus the beam. We have a similar machine from Xtool, the F1, which is a diode-based marker. It uses two types of diodes, a 450 nanometer blue diode and a 1064 nanometer diode. The latter is an infrared diode, used for engraving and marking metals. Each diode and laser requires a specific type of lens, with its own lifespan, parameters, and so on. Let's begin. Carbon dioxide laser tubes operate by utilizing a low-pressure gas mixture, which is made up primarily of carbon dioxide, but also includes other gases that are specifically chosen to enhance the overall gas quality, as well as to improve the efficiency of electromagnetic radiation pumping. These additional gases play a crucial role in optimizing the performance and effectiveness of the laser system. In our case, the laser beam cuts or interacts with certain materials, effectively breaking them down. Let's start with the most common and accessible type, carbon dioxide. Then we'll move on to things like... One of the modern laser sources is the ytterbium laser. The primary pumping medium is actually within the optical fiber. Yes, thanks to the diodes. There are similar lasers, but they're made with a neodymium rod as the pumping medium. These lasers are in medicine and in surgery. Modern women have come up with using lasers for hair removal, epilation or depilation, whatever it's called. Correct me if I'm wrong on that. So to repeat, these lasers are used for marking, engraving, cutting, metal fabrication, and in many other applications. The wavelength doesn't interact with organic matter or certain materials like glass or quartz. Again, lenses made of quartz material are used, or ordinary glass if the power of such lasers doesn't exceed 50 to 60 watts. In all other cases, it's better to use quartz, of course. Using these lenses for other lasers isn't recommended because every laser has its own wavelength, so the interaction is completely different. As for the lifespan of these lasers, the figures vary everywhere. Most manufacturers claim the same thing, that these sources can operate for up to 100,000 hours. 100,000 hours is the figure until total failure. Yeah, naturally, you have to maintain the temperature, humidity, and a precise stable voltage supply. Let's just say there are operating conditions where cold starts without warming up or overheating these sources is unacceptable. Yeah, that figure could start at just 3 hours of life. That often happens with users who operate them while in the wrong conditions, to the point where you could run it for 1,000 hours and make it completely useless. 100,000 hours is the limit for total failure, meaning your source might degrade at 20,000 hours and then run at 10 to 15% of its rated output. If we look at those same neodymium lasers, or lasers with neodymium rods, the neodymium itself is unlikely to fail, but if you overheat it, of course it'll crack. But neodymium sources specifically use quartz lamps. I believe they're quartz lamps with xenon pumping. So basically, these lamps, they fail quickly. They're pulsed and high currents pass through them. And consequently, they burn out very often. So the lifespan of neodymium lasers is completely different. So when it comes to the hours, I wouldn't rely on that figure for this laser at all. Let's look at the option of diode-based laser technology. Yes, it's specialized equipment. It's become accessible because of the low price point. There are no pumping media here. The laser pumping happens right in the semiconductor. The resulting electromagnetic radiation goes directly into the lens and is focused on our target area, or the engraving zone, so to speak. Again, diode lasers come in different types. The first use of such lasers, I recall, was in CD-ROMs, which were accessible to the average person. In CD-ROMs and DVD-ROMs for burning compact discs, actually. That's where we got those little diodes. And we'd set them up with lenses, focus them, and make these micro lasers that we used to light matches or, burn through some paper. Yeah, it was fine. It was cool. Those were, at the time, diodes with a wavelength of 655 nanometers, which is the red spectrum wavelength. Cool stuff. In today's world, there are green, blue, purple ones, so basically whatever kind you want, those lasers exist. It's really great. It's really cool that all of this is available for anyone to buy nowadays. In my childhood, unfortunately, there was nothing like that, and the first laser that appeared in my childhood was specifically a red spectrum laser. It was just a regular pointer we had running on 3 batteries made in China. Yeah, that was really cool. The lifespan of such lasers is, on average, somewhere around 10,000 operating hours. Again, it depends on the power you use, meaning the voltage applied to these, again, lasers. And accordingly, how often and intensely you use it, under what temperature conditions, humidity, and many other factors. So considering the option of buying diodes or diode lasers, yes, you can do that. But you have to keep in mind that, again, depending on the wavelength, it interacts with different materials. That's why I occasionally use a diode laser, like the one from the company Xtool F1. I do some engravings, I'm compensating for the lack of actual CO2 flatbed lasers because those machines really need to be working and making money. Since my products are made in small quantities and released on marketplaces, I use this kind of laser. So for these lasers, specific lenses are used with a certain pump wavelength so that the throughput is, well, the maximum possible. Moving on. A CO2 laser radiation source is multimode. Low-pressure tubes are used containing CO2 gas, or carbon dioxide, with other gas mixtures. Or a metal ceramic one is used. Basically, the design of these tubes can be absolutely anything. Regarding the mode or multi-mode nature, you can't just use any tube length. The tube must correspond to half the wavelength, which in our case is 10,600 nanometers, respectively. And multi-mode, meaning the resonance of our electromagnetic wave inside the very thin tube happens in such a way that the beams bounce in different directions. And only the beam reflected properly and correctly from the back wall due to resonance in our tube gives us the TEM00 mode at the output through a semi-transparent mirror. That is, clearly focused into one tiny little spot. The life of such sources, specifically CO2 radiation for example, a metal ceramic tube comes with air cooling and high pressure. So accordingly, the resource of this gas is much greater and it lasts for a longer time. It can be, specifically metal ceramic, on average from 20,000 hours to 100,000 hours. Again, this is the time until total failure, depending on operation, temperature conditions, power usage, and much more. In this case, glass tubes specifically use a low pressure of this gas mixture. Accordingly, the lifespan can range on average from 1,000 hours to 15,000 hours. Tubes like these, such as LaCia in this case, can work for up to 10 to 12,000 hours. Tubes like the W2, W4, I believe, from the Russi company, we have those as well. The service life can also average 10, 12, or 15,000 hours. Yes, the more expensive the tube, the better it's made. The more a company develops or improves the quality of the gas or gas mixture itself, the longer this laser can operate. Here, the ignition voltage is also taken into account. It's high voltage and, accordingly, the currents that you supply to this tube to ignite the laser radiation source itself. These lasers use only specific lenses that can transmit and correctly focus this beam. Lenses are used based on a zinc selenide mixture. Again, the production of these lenses is a separate, unique process. That is, they're grown here in specific chambers under high pressure and temperatures from two gases. This is selenium gas, and zinc is converted again into a gas mixture, which is supplied for the mixture and the formation of crystal growth. Such crystals look like mattresses. Accordingly, they later cut plates, squares, and cubes from them, and split it. And then they create specific lenses from them, or for use in other fields. There are, accordingly, other lenses made from other materials as well. But lenses made specifically from zinc selenide alloy have become widely used. There, the production says, at least, USA CVD zinc selenium alloy. Lens focus, again, there are different diameters for different machines, for markers, for engravers, for cutting, for cleaning, for anything really. Right. And the focal length is also specified. Focal length, that is, accordingly, from the beam's impact zone to the focus zone. It directly affects, again, the metal cutting thickness, the beam quality, and the engraving methods. You can't use the exact same lens for cutting thick materials and engraving detailed items on the same plywood or certain types of plastic. Don't forget that this design of these, at least CO2 tubes, requires the use of many consumables, such as lenses. They often get dirty, deteriorate, and sometimes carbon deposits or burn-throughs occur. Basically, they either need to be cleaned or replaced. We also have cleaning sticks for sale. Again, don't forget about the mirrors, because if we're talking about fiber optic interaction, metal mirrors aren't used with fiber optics as there's a high probability of damaging them. This wavelength of 1064 nanometers interacts well with metals. With CO2, it's completely the opposite, meaning CO2 doesn't interact with metals. And mirrors are often used, again, made of either copper or other metal alloys that reflect this beam well. Alright, let's move on. On our channel today, I'd like to run some tests and experiments with lenses. We have this opportunity knowing that zinc selenide alloy lenses are often used to change the focal length of thermal imagers. This isn't exactly news, but it's a common practice. In our case, we'll be using a thermal imager from Infrared. It's a standard compact thermal imager that works well and suits me fine, but today we'll try it with different lenses. Let's see what comes of it and how it's all going to work, whether it's feasible or not. And accordingly, we have this green laser here, a green laser pointer that we can test and experiment with to see how well it actually passes through two types of lenses made of quartz and zinc selenide, or a zinc selenide alloy. Yes, this pointer has a wavelength of 532 nanometers, meaning the beam is multiplied by crystals. Resonance occurs within the crystal, and it resonates twice as often. The wavelength uses a standard infrared diode at 1064 nanometers. Basically, it's all simple and logical. Let's get to the experiments and see what the end result will be. So for our channel today, we're going to use a lens with a focal length of 2.5 inches. That's 63.5 millimeters, and the lens diameter is 20 millimeters. We've prepared our thermal imager, set it in position. Now we turn on the phone, and as a result, the imager connects and displays on the screen. I'll say right now, to get a high-quality visualization of the thermal effects, we'll use hot water and turn off any external light sources. There, now everything is clearly visible and looks great. Again, there's a focal length that we can adjust by moving our lens. And often, I'll say it again, those who install these zinc selenide lenses do so to either increase, shall we say, the focal length or decrease. Watch closely. So in our case, everything looks perfect, in my opinion. Yeah. But that's using its native lens. Now let's put on the zinc selenide lens and see how it turns out overall. Now, briefly about the experiment regarding swapping the lens for this little zinc selenide one. I'll tell you right now, if you're doing these experiments, keep in mind that the longer the focal length of the lens you plan to mount on your IR camera, the further away you'll need to place it. This means you'll need to use adapters and set the distance equal to the focal length. So here it's 2.5 inches. Unfortunately, doing all this is difficult. just by hand like this, but again, keep in mind that there's a short focus lens here, and it's better to use short focus lenses here, like 1 inch, 1.5, or at most 2 inches. Again, 2 inches would be about this kind of distance. As you can see, a lens with a focal length of 2.5 inches, naturally, requires placing this lens 2.5 inches away from the object. The longer the focal length we have, the more likely it is that... Let's try to get it in focus. After all, it's practically impossible to do. Probably the only way I could demonstrate how a zinc selenide lens works on a thermal imager is with the example of hairs on a leg. We can focus, say, at a distance like this. Well, let's try as close as we can possibly get it. What does a zinc selenide lens give us? Let me show you. Basically what electronics technicians mostly use it for. By installing a zinc selenide lens on our thermal imager, we can get an increase of almost 10 times, greater or higher compared to the same standard classic lens. Yes, and that's not the limit. You can do more, increase the focal length, and, well, get a much better result. But even so, we can already see that a detailed view of some small elements under the thermal imager will be much better and clearer. More detailed, let's do a simple test using our green pointer, that is, our green laser, for 2 types of lenses, for fiber optic lasers and, well, for CO2 on a zinc selenide alloy. Naturally, we won't achieve any special result here because there's already a focusing lens that actually forms the beam itself. And that's how it all works. If we use a classic lens from the same fiber optic marker, then accordingly, the beam formation, nothing will happen here. Nothing will be formed, it will reflect off other walls, other lenses, filters, and much, much more. And we get, accordingly, this kind of scattered mode, if you can call it that, to be more precise. But despite all that, it all focuses a bit unstably. Yeah, you can set up a nice light show, point it at the walls, basically form whatever you want, but we don't achieve the result we need, which is getting a thin, focused beam, or, say, getting some other specific beam shape. If we use a zinc selenide alloy, or in this case, it's a lens specifically for this wavelength, then, accordingly, it's the same situation. We don't get a decent result, or the required beam quality, and our beam just scatters in this medium, in this, let's say, composition. There, I hope you can all see clearly what's happening. The process isn't really focusing this lens well. Yes, there is a focal length. Even if we set it here, shorten it to our 2.5 inches, we won't end up with our beam cutting the table, or marking, or engraving these specific positions. Don't forget that each lens is used for specific types of machines. If we're talking about markers, then the f-theta lens, which the plane specifically in the focal beam, goes with the convex part down. If we're talking about non-markers, specifically flatbed engravers, they use lenses with the convex part up and a perpendicular beam down for focusing in the cutting or engraving zone. Guys, well, basically, today we experimented, played around, looked at possible options, tested today on a thermal imager, looked at types, sources, their lifespan, accordingly, showed the consumables, how it all works, how it's all set up, what it consists of, and how it all looks. As always, a big thumbs up from you. Today with you was Igor, Gravity Engraving channel, also the T-Opple channel. So similar videos of specifically good quality, without swearing, without cursing, will be released on 2 channels simultaneously. Regarding consumables, I'll leave lists in the description to this video. Phone numbers will also be in the description. For those who will be purchasing laser tubes, only for this first batch, the dates are all completely fresh. Prices will be at a discounted 10%. Good mood to everyone, and as they say, more goodness, cash. Bye-bye, everyone.